Hey folks, this is Captain Jones here to talk to you about Turing machines. This is going to be a brief interlude to elaborate a little more on conceptually what is a computer, what is it about the little man computer or the LC3, which is the computer. We'll spend the majority of this class looking at what makes them actual computers as opposed to just simple calculators or something. Okay, so our objectives today are twofold. We're going to try to define the term computer, define what makes a computer, and along the way, a very important thing to understand is something called the universal Turing machine. So we're going to describe that as well. Okay, so if we take sort of a first stab at defining a computer, we get a helpful definition in the companion book, Basic Computer Architecture. The author says a computer is a general purpose device that can be programmed to process information and yield meaningful results. And so you can see a little example graph here on the left. Our computer is the thing in the middle that takes in these two types of inputs, a specific program that tells it what to do, and the data or the information that it's operating on, and the output of that is going to be some result. And the computer is configured in such a way that the program and the data can change without changing the computer, and it can do different things based on those two things. So that's a nice broad definition for a computer. It doesn't necessarily help us kind of define what is a computer. So we're going to take sort of a second pass at this, aided by a gentleman named Alan Turing. So Alan Turing was a computer scientist in the 30s and 40s, brilliant scientist who helped break the German Enigma, and by some historians was credited with shortening World War II by up to as much as 2 years and saving many millions of lives. And in his seminal paper, he took a stab at sort of trying to define a computer by starting with this thing called a Turing machine. And so keep in mind, this is the 30s and 40s. We are not at our electronic devices yet. We haven't even seen a transistor. So his definition for something called a Turing machine was to imagine a piece of magnetic tape, like you might find in a cassette tape, that's infinitely long in each direction. And the machine's composed of this tape head that can read a symbol at each location on the tape, and which can move left and right. There's a little piece of memory that stores which state the machine is in, and the operation of the machine is defined by an action table, which effectively lists 5 things based on the current state of the machine, and the symbol underneath the tape head. So that would be the symbol on this piece of magnetic tape. The Turing machine can move the head left or right. It can write a new symbol on the tape, and it can also transition to a different state. And with enough of these actions, this is basically a finite state machine, right? With enough of these actions, Turing said you can make a Turing machine do a number of very useful things. An example here is given from our textbook, where we could hypothetically define a Turing machine that performs addition on 2 numbers, or a Turing machine that performs multiplication on 2 numbers. And that's useful. Turing went on in his paper to define something he called the universal Turing machine. This is the important one that actually kind of gets to a computer. So Turing said, okay, if we have this idea that a generic Turing machine, we could imagine also that instead of sort of hard coding in that action table the things we wanted our computer to do, we could instead sort of compose a generic action table that performs a handful of hard-coded useful things, and instead sort of is modified by this part of the tape called a simulated action table. So this is part of the tape that sort of defines new actions potentially, and you could orchestrate this this Turing machine so that sort of given a symbol and a state that we're in, the Turing machine would look into the simulated action table for instructions on what to do next. The simulated action table could then define what the tape head should do. So then the Turing machine would come back to where it was and potentially rewrite a new symbol or move the tape left and right and then proceed with its operation. Kind of a block diagram of that here shown in our textbook, where we have this thing called the universal Turing machine, where the operations that we want it to do are defined as inputs to the machine. So T add, T mul, these are the adding and the multiplying sort of conceptual Turing machines we saw on the previous slide. These would effectively go into the simulated action table. And then when we provided our universal Turing machine with a series of inputs that would go into the work area, then the output would be our desired operation. And so this in effect is a computer. Actually, what I want to do is I want to say okay, and Turing further proposed. And so the last critical piece of this is that Turing proposed, I want a definition down here, that a universal Turing machine is capable of computing any computable problem. And this is a funny statement because, for one thing, there isn't a real strict definition of what a computable problem is. We kind of understand conceptually that addition and multiplication are computable problems. It's less clear that like video streaming is a computable problem, but we know that to be true because our computers are performing it. Furthermore, there's no proof of this statement at all. Turing sort of proposes it. And it's one of those things that the world has come to accept, although there is no proof that a universal Turing machine can compute any computable problem. But it's just that the more computer sciences develop, the more we find additional evidence that this is true. And so a universal Turing machine, or something that looks like a universal Turing machine, is in effect a computer. So this provides us with a slightly more specific definition, which is not just that a computer is a general purpose device that can be programmed to process information and yield meaningful results, but also that a computer is a device that can compute any computable problem, or in other words, it's a device which looks like a universal Turing machine. The last important piece that came out of Turing's work is the idea of Turing completeness, and Alan Turing showed in his paper that not only can you define this machine here called a universal Turing machine, which is able to simulate other Turing machines, but he demonstrated that a universal Turing machine can't get any more capable. If you try to create a universal Turing machine that's more capable than a different universal Turing machine, you just get the same universal Turing machine. And so if we can prove that the little man computer here is equivalent to just a generic universal Turing machine, and we can also prove that our Mac laptops are equivalent to the same universal Turing machine, well, what we've effectively done is shown that the little man computer is every bit as capable of the laptop or the desktop, that's sitting on your desk. And the only this may seem incredible. The only two caveats that'll probably help explain this is that we say that the little man computer and the laptop are equivalent if given enough time and memory, and those are two really big caveats, right? So what we're saying is that there is nothing mathematically, conceptually different about these two computing devices that lets one do any more than the other. But the Mac laptop, or whatever's laptop is on your desk, is able to do things faster and more efficiently, using less memory, and that's what makes it a more desirable device than a computer that is implementing this conceptual model of a computer, the little man computer. So these two devices functionally are equivalent, given if and are functionally equivalent, and would be exactly equivalent, or are equivalent if given enough time and memory. Um, yeah. Okay. So to summarize, we started by trying to define what a computer is. We have this generic description given to us, which is a computer is this device in the middle, a general purpose device that can take in some kind of program and some amount of data and produce meaningful results based on those two inputs. A slightly more concrete or formal definition is provided to us by Alan Turing, who said, well, a computer is anything that looks like a universal Turing machine, which is to say anything that can compute any computable problem. And furthermore, a universal Turing machine is as high as it gets. If I've got something here, like my little man computer, and I can prove that it is equivalent to a universal Turing machine, and I have my M1 laptop that I can prove is also equivalent to a universal Turing machine, well, it just follows then that the little man computer is equivalent in computing power to my Mac laptop, with the caveat, if it's given sufficient time and memory. And so, yeah. So maybe the last thing I want to say is, so then when we look at the LC3 a little later, you'll see something that kind of sits in between these two computing devices. It's more capable than the little man computer, but it's not going to look quite as capable as the laptop. The thing to keep in mind is that the LC3 is functionally equivalent. We can show, we're not going to, but we could conceptually show that the LC3 is equivalent to a universal Turing machine, meaning it is every bit a real computer as the one that's sitting on your desk right now. Today's quote is brought to you by Michael Jordan, who said, I've missed more than 9,000 shots in my career. I've lost almost 300 games. 26 times I've been trusted to take the game-winning shot and missed. I've failed over and over and over again in my life, and that is why I succeed. See you next time.